Hi, we are starting our last unit with this lesson. Unit 5 is going to be about probability to some extent, so that's actually where the unit begins. We will then move on to talk about combinations and permutations. You might have some knowledge of this from another math class that you've taken. Then we'll be talking, our last two lessons are about, our last two pieces are about different kinds of distribution. So we'll be talking about the binomial distribution as well as the normal distribution, and that is it. So basically like four more-ish things to learn depending how you count. So if you were disappointed in your results on the Unit 4 test, please just make sure that you get in touch with me and just email me. We'll set up a corrections conference and you can use that as a way to improve your test grade. If your test grade was low enough that it would have lowered your grade from March 12th, pre-COVID-19, if that is the case, then your test score is marked exempt. It is not included in your grade calculation. However, some of you are really using this opportunity to try to improve upon that grade, and so you might be interested in having a test conference with me. And so if you get your test score to be higher than what you had on March 12th, then it would raise your grade. So that would be a good thing. All right, so just let me know if that's of interest to you. Okay, so we're going to start our notes today with thinking about what we have already talked about. So in Unit 4, we talked about some problems that were find the probability of event A or event B happening. And the formula that we should remember from that situation is the probability of A plus the probability of B is a way to deal with an OR question. So OR in probability life indicates that you're supposed to add. Now, there was a condition for that formula being true. It wasn't true for all times. And the condition for that was that A and B had to have no overlap. And the term for that is mutually exclusive, or a synonym for that is disjoint. And if you were to draw two disjoint events in a Venn diagram, they would be like this, completely separate. They don't have any outcomes in common. However, sometimes we do want to find the probability of A or B, but there is some overlap. Okay, so sometimes, like back in this picture, if I were to ask you here in this picture, what is the probability of A and B? You would say 0 because there's no overlap, right? There isn't anything that they have in common. So what I wrote here is that sometimes that A and B is something other than 0. In other words, there is some overlap. But sometimes we still want to find the probability of A or B, even though those events overlap. So can we do that? The answer to that is yes. And if we were to add those together, we're going to get too much. So if you look at this particular problem, if I find the probability of A here, and I didn't give you any context for what this means, but let's just say there's 10 ways for just A to happen, there's 3 ways for A and B to happen, there's 12 ways for B alone to happen, and there's 7 that are outside those two, okay? So if I were to just find the probability of A, I'm looking here at circle A. You might remember we had a lesson where we like shaded in different parts of the Venn diagram, right? So if we were to just color in group A, we can see that that's 13 out of our total. Our total's 32. And then if we're looking at B, well, here's set B. And if I were coloring that part in, that would be all of this. Okay, so set B has 15 out of 32. And then if we did that math, we'd get 28 out of 32. Now, without doing that calculation first, I might have looked at my picture and said, okay, being in A or B would be all of this. And if I just add together those three distinct numbers, 10, 3, and 12, I get 25. So 25 out of 32. Now, this actually is the right answer. This is not right. So what is it that makes us be off? I'm off by 3. It's the overlap that's making us be off. Because if you think about it, that 3 got included in set A, and then the 3 got included in set B. And you can't count the 3 twice. The 3 just is there the single time, right? It's in the overlap. It's not there twice. So the overlap is what makes us be off. So here's the suggestion I would have, okay? So if A and B are mutually exclusive, like in the last unit, just stuck with that case, then you're just going to take the probability of A and add it to the probability of B when you want to do an OR problem. However, if they are overlapping events, you'll still start out the same. It's nice to be able to start the same, but you want to adjust for that amount that you're off by. And the amount that you were off by was the amount that was in the overlap, because the overlap is going to be counted within both of these. So just subtract off that overlap. Now, honestly, this formula that I just wrote in purple would work for this top case as well, because in the top case, that part that I just dotted underlined is 0. And so subtracting 0, fine. That's the blue formula, okay? So it's actually the purple formula that's at work all the time. It's just that sometimes there isn't an overlap, and so that last term is 0, okay? So this is the most general situation. It will work all the time. This blue formula will only work if the two groups are separate, if they are disjoint. Okay, that's the first idea of today. Here's the second one. The second idea has to do with when you have an AND problem. Now in Unit 4, we said it's an unusual situation in math. Usually AND means an addition sign, but in probability AND means to multiply. Just make a note of that. Okay, so AND means multiplication in probability life. Okay, and we did this formula already. Now there was a condition on this. The condition was that the two events had to be separate from each other, and we called that being independent. So the probability of B is not affected by what happens with event A. Okay, so A and B had to be independent. And we talked for a while back in Unit 4 in one of those videos about how independent and mutually exclusive are not synonyms, okay? They mean something completely different. Okay, now, however, just because that formula works for independent events doesn't mean that everything's independent. That is false, okay? So sometimes we do have two events that do influence each other. And if they do influence each other, they are called dependent events. They depend upon each other. So for example, easy example to think about is the deck of cards, okay? So think about a deck of cards. I pick a card and I keep the card. And then I pick a second card. Now by keeping that card, the deck no longer has all of the choices available anymore. What happens second depends upon what I drew first. That's why we call it dependent, right? It depends what happened first. So if I'm trying to find the probability that I draw a heart and then another heart, this is what I do. It's still going to involve multiplication. And the first part of the problem is still going to be the same. It's the second part that's going to change. Okay? So what is the probability of drawing a heart? Well, there's 4 suits in a deck of cards. which means out of the 52 cards, 13 of them are hearts, right? 13 times 4 is 52. So 13 hearts out of the deck of cards. Now, I keep that first card, and I want to think about that second card now. Well, for the second card, I'm going to have one fewer possibility because I already have a card in my hand, right? I'm already holding on to one. That card can't be picked again. Furthermore, in order to end up with 2 hearts, this first card has to be a heart. If the first card is a club, can I end up with heart, heart? No, I cannot. Okay, if the first card is a diamond, can I end up with heart, heart? No, the first card is a diamond, right? So you have to assume that the card that you picked first worked out, and then think about what would have to happen for the second card. So if the first card was a heart, how many hearts are available now? Should have thought 12, right? Because one of them already was selected. So this second piece is what we call a conditional probability. It is the condition in this problem. It is the probability, I should say. Let me try again. In this particular problem, the thing that I put red around is the probability of drawing a heart on the condition that the first card was already a heart. So you would just do the arithmetic here, but let's talk about the formula, okay? So the second part is what we call a conditional probability, and we did that already when we studied two-way tables. We did actually talk about conditional probability back in Unit 2. So to summarize the two formulas for AND, both of these are for AND, we do probability of A times probability of B under the condition that A and B are independent. That's what we did in Unit 4. And the new thing that we just learned today, okay, get ready for some notation. Here it is. The beginning of the formula starts the same. Both these say probability of A. This part, you'd say the probability of B given A. Find the probability of B assuming that A already happened. Another notation you sometimes will see for this B given A is as follows. You sometimes might see this formula written as probability of A times probability, and then sometimes just a vertical line is used right here for the word given. Okay, so those are two formulas for and if you think back just a moment ago, we had the two formulas for or right here. So all told, that's 4 formulas. Okay, you can certainly have those out in your notes when you take the unit test. I would recommend that. Okay, there are 2 formulas that start out with or. Notice the left side of the equations, right? This is for mutually exclusive. This is for overlapping. I said actually you can use the red one for everything, for all or problems that would work, because this part would just be 0 in the other case. And then these are the 2 formulas for and this one you kind of can't mix them up. But independent events, you want this, and dependent events, you want this, or whichever way you like it, with the word or with the line. Okay, so this bit is just to remind you, I did mention that we did conditional probability back when we did two-way tables. So I thought I would give you a two-way table question and just let you see, because this is actually technically a review. Okay, this isn't an and problem on its own. This is just working on the conditional probability part. So the conditional probability part is just figuring out like this piece or this piece. Okay, so I would like you to pause the video here and then come back in a second and see if you got the question right. Take a second and write down the question, right? There's a two-way table here, and then there's 4 questions in purple that I'd like you to try. Okay, so you can see in the 2-8 table, I highlighted the bottom because those were totals. I also noticed that because I didn't have a column that said total, I did have to make some row totals, and those are off to the edge. Now notice with each of these, given the fact that they're conditional probabilities, this given adult means that I'm going to have the number of adults at the bottom. And then within that group of 119 adults, right, and I know that these refer to adults because of the labeling, how many of those 119 liked chocolate? So that's 55 out of the 119. Then the rest of them work very similarly. I do think that these last two in relation to each other are a nice compare and contrast. So probability of child given vanilla means you have the vanilla subgroup. And then within that, you're going to have 22 out of those 92 who are children, okay, within the vanilla group. This last probability says given child. So assuming you have a child, so that would be within this group, that's the 77 that are in that top row, how many of them like vanilla? It's 22. So you can see within the last two questions, a 22 is consistent, right? That is like overlay of child and vanilla, but it has to do with the total changing, right? That's the given part that had to change. All right, so hopefully this little bit just reminds you that you have indeed done this before. Back in Unit 2, if you have your binder at home, you can take a look back in Unit 2 near the end. We did these conditional probability kinds of questions. And again, just to reiterate, the reason I'm bringing that up is because this part of the problem makes use of a conditional probability, okay? So your assignment is problem set, the problem set that is listed for today. Remember that you have your presentation of your project with your group online with me this week. I'm very excited about that. I think actually I meant to check this before I sat down to report. I don't have it right in front of me, but I think your homework set uses the words prime and composite. I think that's today. And so just in case, prime are numbers like 2, 3, 5, 7, 11, 13, and so on, where the only factors are 1 and itself. Composite are numbers that are composed of more than one thing. So for example, 4 is a composite number because it's composed of 2 primes. 6 is a composite number because it is composed of 2 primes, and so on. Okay, so I think that's today that definition comes up. Okay, so in case you need it, there it is. In case you don't, fun math fact. Thanks so much for listening and continuing to be a good and dedicated student. I miss you guys.